So the next example we're going to do is we're going to describe our voltaic cell based on these two reactions. So we need to describe a voltaic cell based on, and we're going to use silver again, where we have silver plus ions in solution plus an electron is going to give us silver solid. Our reduction potential for this particular reaction is 0.80 volts. The other half reaction we're going to analyze is iron 3 plus in aqueous solution plus an electron becoming iron 2 plus in aqueous solution. The reduction potential for this half reaction is positive 0.77 volts. So the first thing we need to do is recognize or identify the half reaction that's happening at the anode and the one that's happening at the cathode. So find the most positive cell potential, which in this case is positive 0.80 volts. And we know that this reaction, or the silver half reaction, has to occur at the cathode. That means our second reaction with our iron occurs at the anode. If we're setting up this cell, we have the anode over on the left and the cathode over here on the right. We set up the cell where we have two beakers, and the cathode material is going to be the same thing from the previous question, or the previous example, where we have silver solid. And then we're also going to immerse that with silver ions in solution. In the case of the anode, we have two ions in solution. So what we typically observe is we'll put some kind of platinum wire in here and then connect that through over through the voltmeter. And then in this solution, we're going to initially start with a 1 molar solution of iron 2 plus and a 1 molar solution of iron 3 plus. We add our salt bridge, and now we have our cell. But we need some kind of conducting solid here, which is typically platinum. The only drawback from using platinum is that it's so freaking expensive. So here's how we would set up or describe this cell. Now we can break it down into the two half reactions. So our oxidation half reaction, which will occur at the anode, is iron 2 plus in aqueous solution becoming iron 3 plus in aqueous solution plus an electron. Our potential for this half reaction is going to be the opposite of the reduction potential, which is negative 0.77 volts. Our reduction half reaction is going to be our silver plus in aqueous solution plus an electron, giving us silver solid. The potential for this reaction is going to be the reduction potential, which is positive 0.80 volts. The electrons cancel out, and this gives us an overall reaction of Fe2 plus in aqueous solution plus silver plus in aqueous solution, giving the products Fe3 plus in aqueous solution plus silver solid. Our cell potential for this overall reaction is going to be positive 0.03 volts. So this is a considerably smaller potential than what we saw in the previous case where we used silver and copper. So what we're doing in these cases is observing these electrochemical reactions. We can observe an electrochemical reaction by taking a strip of zinc metal and putting it in a copper solution. But by doing that, we're not really creating any electricity, or we're not able to harness that electron flow. So if we set these up into these two separate cells, or create a cell from these particular reactions, and put the salt bridge in there, we can create that electron flow and use that in a better way. So we'll pick up with these electrochemical relationships on Monday, and I hope everyone has a great weekend.